Hello and welcome to Lesson 8. In Lesson 8, we look at balancing chemical equations, a topic that most students coming into IB Chemistry have had some exposure to it already, unless you're coming in without having taken chemistry in years 9 and 10. But once you've taken some chemistry, most likely you would be familiar with how to balance a chemical equation. But what is the point of balancing a chemical equation? Why is it that we need to write equations using symbols and numbers? And why is it not possible to stick to writing an equation like this one here? Carbon, like charcoal, solid carbon, that's what this S stands for. Burns in oxygen, oxygen gas. That's what this G stands for. So the carbon is set on fire, a piece of charcoal you can think about, set on fire in air, and then what happens? It produces a gas, carbon dioxide, and here you have CO2 gas. So why can't we stick with this equation? And we certainly can. We can say that carbon or charcoal burns in air to produce carbon dioxide. That carbon dioxide goes into the air and it's consumed by plants in photosynthesis, or it adds to the greenhouse effect in the atmosphere, and we are concerned about burning coal, which is charcoal, and we can go on to have a pretty good understanding. But what if you wanted to predict how much carbon dioxide gas would actually go into the air when you burn 1 ton of coal, or if you burn 60 grams, let's say, of charcoal, pure carbon? Then writing an equation like this would not lend itself for you to track where all of the matter goes, because the law of conservation of energy states that matter and energy cannot be created nor destroyed. So that means that whatever matter and energy you have in carbon as charcoal and in the oxygen, that matter and energy has to be transferred somewhere. And if we are concerned about the matter, it means that all of these carbon atoms and all of these oxygen atoms that are consumed need to go in to some product, and that product is CO2. Now, if we know the actual mass of charcoal, let's say it's 60 grams that we burn in air, and we burn that in an excess of air, it would consume oxygen from the air. And then the thing that would determine how much CO2 you get would be how much charcoal you have. When the charcoal is burnt out, the reaction is finished. So we would then say that the charcoal or the carbon is the limiting reagent because you're using an excess of oxygen. Balancing this equation is very important because we will use what we learned previously about how to convert mass to moles and moles to mass, and what we learned about 1 mole of a gas to predict the actual amount of carbon dioxide. But balancing the equation, likely you're familiar with that, but let's look at this equation though and see if it is balanced first of all. And to check if an equation is balanced, or to balance any equation, the only place that you're allowed to add numbers, whole numbers, integers, are in these places with green. You might see in books that equations are balanced with fractions, and that is sometimes used to help in your understanding because it really is just about a ratio. But a standard way of writing a chemical equation is to use whole numbers or integers. So here you have 1 carbon atom. I know that because there's no number before here. If there's no number written, 1 is understood. And that 1 carbon atom reacts with 1 molecule of oxygen. So O2 tells me it's a molecule of oxygen to give 1 molecule of carbon dioxide. Another way of saying it is to say that 1 mole of carbon atoms reacts with 1 mole of oxygen gas to produce 1 mole of carbon dioxide. So this equation is balanced as it is. But remember I said 60 grams of carbon. So if we go back to our previous lessons and look at how to convert 60 grams into moles, you would recall that you divide the mass in grams by the relative atomic mass of carbon. And 12.01 is the relative atomic mass of carbon as given in the periodic table. 60 grams, it would come to approximately 5 moles. So 5 moles of carbon would burn, and it would react with 5 moles of oxygen, because that ratio is 1 to 1. So if this becomes a 5, this would have to become a 5. And then you would get 5 moles of carbon dioxide. And if you know the temperature and you know the pressure, then you can use PV equals nRT to solve for the volume of carbon dioxide. Or if you're told that it's standard ambient temperature and pressure or standard temperature and pressure, then you can more readily just multiply accordingly and solve for the volume of carbon dioxide. I'm going to pose some questions like this for you in the worksheet that follows up with this lesson. But let's look at some more equations. Here you've got another one. Methane gas. Now that's something, if you don't know what methane gas is previously, we'll need to provide you with the formula. Methane gas, a hydrocarbon, CH4. It burns an oxygen, O2, to form carbon dioxide, gas, and H2O gas comes off as water vapor and goes into the atmosphere. Is this equation balanced? How we go about it? We see that there's CH4, one C over there, one C over here. 4 H's though, and 2 H's on this side. So the first thing we might think is we need to put a 2 here. When you balance equations, to remind you, the only place that you're allowed to add whole numbers or integers are in these green spots. You can't put numbers down below as subscripts, and you can't put numbers in between, only at the front of a formula. When you put a 2 in front of this H2O, that 2 is multiplied by this 2 to give a total of 4. And then that would balance this hydrogen with that hydrogen. Then you've got O2 here, and you've got O2 here, and you've got 1 O here. But this 1 O that's understood has to be multiplied by that 2 that you've put in front here. So that makes this 2 oxygens, 2 multiplied by a 1 that's understood here. That's another 2. So that's 4 oxygens now on this side. So we've got to balance on this side. And we are allowed to add a 2 here. So oxygens have balanced 4 plus 2 plus 2, that's 4. Hydrogens have balanced 4 hydrogens, 4 hydrogens. And carbons have balanced. So the balanced equation here says that 1 mole of methane gas burns with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. So if this entire thing is done at standard ambient temperature and pressure, let's say, and I use 24 liters of methane or 1 mole of that gas, then I'll automatically know that I'll get 1 mole of carbon dioxide and 2 moles of water. And that, of course, is why we need to balance equations, and we need to write chemical equations so that we can then use what we've learned in the previous 7 lessons to apply it to this concept of knowing what we put in to predict what we are going to get out. Moles to mass, mass to moles, balanced equation. And bringing all of those together, we are going to be, it means we are engaging in the science of stoichiometry, making predictions of how much of a particular product you would get based on the amounts of the reactants that you have. But to go about implementing it, we need to put all of these pieces of the puzzle together. Here we've got another 2 equations, and you should be able to see that both of these are already balanced. But going back to what we did in the last lesson, we need to first be able to write the formula for calcium carbonate using this polyatomic carbonate ion and knowing how we combine it with the calcium ion. So that's another of our previous lessons that we need to draw on. And here you should be able to realize that this equation is already balanced, and so is this one. This one requires a high amount of heat to decompose calcium carbonate. And this one, likely familiar to some students, a base plus an acid to give us salt and water. And again, you'll be able to inspect this and see that this is already balanced. One sodium, one chlorine, two H's, two H's, one oxygen. A balanced equation. Here the state symbols says AQ. That's for an aqueous solution, something that is dissolved in water. And here water is produced as a liquid. If you're having any problems balancing equations, it's really important that you spend some time practicing. And if you click on the link below this video on YouTube, or on the link that I will provide you on the additional worksheet, you'll be able to go to PhET simulations and get some very useful practice with balancing chemical equations. But in the next lesson, we look to bring all of these 8 lessons together and apply them to solving stoichiometric problems.